Hi, Professor.
Yep.
Yeah, one quick question about the last week class. Yeah, you
Sure.
said that we have to send the answer of the binary conversion through email to you, right?
Yeah, it was part of like the
Yeah,
in-class work.
yeah, but you replied to me like there's something missing because I didn't submit my answer because I was confused about the binary conversion. I didn't know the answer, so I just sent an email about the June 2nd class attendance.
Okay. Yeah. So did you get a better understanding from the recitation?
Yeah, totally.
Okay. No, that's fine then.
All right, thanks so much.
Yep. Okay. Welcome back. Hopefully people had a good weekend. And I suspect a lot of you coming from recitations right now. I think there should be a little gap between. So hopefully you had a chance to rest up before hopping into this class. As I mentioned from last week, I'm going to have a little in-class work, sort of goes towards like same thing as like last week with the numeric conversion, sort of like a little extra credit, but also help you to prepare for the exam and just give you a break in between because I know 2 hours is a long time. So we'll be doing that. So just a couple of things before I get into things. So you probably may have noticed I do send out the announcements. I guess you wouldn't be here if you didn't catch my announcement. So I am sending out the announcements that kind of goes into the Zoom class and the password. So at least on a weekly basis, if not on a every class basis, I'm supposed to change the Zoom ID and the password. I'm still going back and forth whether I'll do that or I'll just set the one Zoom ID and password for the week or not. But if you see a different one, I'll send it out from the announcement. So that's that. Some of you, I don't know if you saw this announcement, but I put out there that I was reviewing, just double check on the introductory assignment. Let me go into student view and I'll see what you can see. And you click here on the left-hand side where you see assignments. And you can see the introductory assignment. So introductory assignment is a very basic thing. You can always pop into our office hours. One thing I've mentioned about the office hours is that I posted my office hours and also the TAs have posted their office hours. But do try to send an email or something to give us a heads up that you're going to show up, because I try to make sure that people don't all jam into the office hour at the same time. So I might kind of get someone to do like office hour at whatever, like 3 o'clock. And then I might schedule the next office hour person for like 15 minutes later, just so that everybody doesn't kind of show up at the same time and end up sitting like waiting around or listening to other people with questions. Okay, so do that, and we'll be able to answer any questions to do your introductory assignment. So you should see that when you click on the assignment here. Okay, let me leave the student view here. And I also mentioned Piazza for those of you that don't know, it's right here. So you can click on Piazza, and it's similar to some of the other chat things where basically you can post questions that you have. Like hopefully there's other people that may have the same questions so that you guys can all share some of like the knowledge from that, right? Maybe someone else actually has the answer to it. You can answer it right there. I've asked the TAs to monitor the Piazza forum on a regular basis. I also look at the Piazza forum on a regular basis. And we try to answer them fairly quickly. Of course, I also answer the emails fairly quickly also. So, use the Piazza as a resource when you have questions, get it out there, don't suffer in silence, okay? I think I mentioned last week or last lecture about performance evaluations or feedback. We encourage that. So there will be a survey that kind of goes out and people will get a chance to talk about what they like and what they could, use improvement in the class. And, we do take it pretty seriously, and it factors into like how things are done in the following semester. So maybe we change the way we handle some assignments, or we change the way how we handle some of the exams and whatnot. But that doesn't really do you much good if you give me feedback and we incorporate it for the next semester. So if you do have feedback, do send me email, and I'd like to try to address it as a part of this class. So if there's things that you think we could be doing better, or you're having some challenges, send me an email, and we'll do our best to try to make adjustments as we go. So you can get immediate response or improvement based on your feedback for this semester rather than benefiting the next semester. Okay, so the other thing I did is if you go here under allow section 6 to 8, so what I've done is I did the link to recording of the intro lecture, and I've also put in the slides, so chapter 2 and chapter 7, which is last week, and you can see just some worksheets you can practice with. There's a couple of games here that you can do to practice this. There's a reference on the binary hex conversions in Khan Academy. And then we also have a tutorial here. And then I know this lecture from last week was like just one long lecture. So what I did was I actually pulled in like clips from my earlier lectures from last semester, which is basically keyed by subject or topic area. So you can go in there, so you don't have to kind of go through like the long lecture and try to figure out where a topic is. You can go in here and pull out the different things that you're looking for. Okay, but these are just recordings from last lecture, last semester. Okay, and you can see I have that for June 2nd. Okay, and then I set up for June 7th. So what I did for this week, we're going to cover chapter 3, 4, 5, and 8. I put in a W3 school reference. That's for your HTML. We talk about how the search engine works, and then IPv4 versus 6. And then same thing as for the prior week, I'll be having old videos, which is basically keyed by the topic in small little video clips that you can take a look at. So June 2nd week, June 7th week is set. I haven't gotten around to organizing these other ones, but I left them here. So if you want to jump ahead, you're welcome to jump ahead on these, but I'll be organizing these each week as we go. Okay. So really quickly, I'm going to just go over here to the binary conversion practice. I know kind of happens every semester. We have like, some questions or some trouble around it. So between the recitation and between like the resources we put out there, hopefully people have plenty of opportunities to get some practice with this. Okay. And I think like at the end of last week, I tried to draw the analogy between like the binary system and the decimal system, and hopefully people can kind of get some idea based on drawing that analogy. But let me go into this binary conversion practice. So here's one of them. And so if I hit run here, So I think if you remember last week, I was talking about how you take like the biggest number, right? So this is a decimal number, right? 120, right? And you remember we were saying for all the exponents of like binary, which is 2, you'll go 1, 2, 4, 8, 16, 32, 64, and 128, okay? And so if I look at these numbers and I look at this number, I kind of compare, well, what's the biggest number that I can get to without exceeding 120, right? So I look at this, well, it looks like 64, right? Because if I do 128, that's obviously over 120, right? So then I'm going to click on this, okay? So you can look at it as almost like filling in the pieces of the pie, right? So 64, what remains left to get up to 120, okay? So if I take like 120 minus 64, then I have 56, right? So if I have 56, what is left over that can fit in here? Looks like 32, right? So then I get to 96, which is good, right? If I clicked on, let's say I clicked on 128, it would have been a bigger number, right? So 64 plus 32, right? 64 plus 32 equals to 96. So what's left? I have 26 left over. So what's the biggest number here left? I have 16, right? So I can go 16, and then that all adds up to 112. You can start to see how you have this 64 plus 32 plus 16. That's the same thing as me going from binary to decimal conversion, right? I'm just adding up these powers of 2. So this 112 to 120, I have 8 left over. And magically there's an 8 here, right? So I can click on that 8, and then that matches up. It kind of flicked on the screen pretty quickly, but that's kind of how you look at a decimal to binary conversion, right? I mean, that's one way to do it. That's the way I tend to do it. There's also the example that was in that PowerPoint that basically just like did everything divided, and then you just kind of fall to the right. So that was an example there. I'm pretty sure in recitation, the TAs must probably review that method also. It doesn't matter. You can use whichever one you feel good with, right? But there's just one game that kind of tries to help you practice that idea, okay? And we go back to here, and then you have this one here, okay? And this one is to kind of help you go from the binary number to decimal number. So you can see it just does the first 3 numbers here, right? So 1, 2, and 4, okay? So you can just kind of say, well, if I add, let's say this is a 1, 1, and 1 in here. That means I'm adding 4 plus 2 plus 1, okay? So my internet connection is unstable. I don't know. Okay, so that means if I add these numbers together, then I want to try to find one of these numbers, right? So for example, I see 3 here, right? So 2 plus 1 equals to 3. So I want to see a 0, 1, 1. Okay, so where can I see a 0, 1, 1? Here looks like a 0, 1, 1, like that. And then it crosses off the 3, okay? The next one is 5, right? So 4 plus 1 equals to 5. So that means a 1, 0, 1, right? So where's a 1, 0, 1? Here's a 1, 0, 1. Then you have a 5. And then this one's easy, right? That's only a 1. So that's only here, right? So I want a 0, 0, 1. And that's that. And then a 0 is obviously 3 zeros, right? So then I would just take 3 zeros like that. And then this one is a 2. So it means I want a 0, 1, 0. So that would be this one here. Okay. So hopefully people get the idea. I know it's a kind of a simple game, but hopefully you can get the idea of this idea of decimals to binary and binary to decimals. This gives you some practice here. So I'm going to let you guys do a little bit of this during our break, our 10-minute break between the lecture chapters. Okay. So you can get to that here within the resources. Okay. So here and here. There's worksheets here. You can practice that. There's the Khan Academy tutorial, like I said. Here's another tutorial here. Okay. So hopefully that's, a number of different ways to get to understand how to handle the numeric conversions. Okay. So with that, let's go ahead and pick up a couple of things for the next chapter. So as you can see, we have 3, 4, 5, and 8. So what I'm going to do is I'm going to pick on chapter 8. I'm not going to get into the HTML stuff until Wednesday. So we'll hold off on that one for a bit. So let's take a look at this. So you remember at the end of last week, we were talking about like how you can do perfect reproduction with digital, right? Because digital, you're basically copying zeros and ones, okay? And there's a lot more to it than that. Like you can do a lot of different things with it. And we also talk about like, well, okay, I can do perfect representation, but at what level of granularity I can capture the information, right? So I can capture something as black and white, right? It would be less information, right? Maybe not as quote unquote accurate, but people might do that for whatever reason, right? Maybe they're trying to save space and stuff like that. So in that case, the more information you put in the different dimensions, the more accurate your representation will be, whether it's for video, whether it's for a picture, or whether it's for sound, right? So when we talk about multimedia data representation, that's what we're talking about. We're talking about sound, we're talking about pictures, and we're talking about videos, right? And all of these are kind of different terms that relate to those concepts, which I'll be talking through in a second, okay? So let's get up to the top here. All right. So this is just like what I was saying before, right? We have pictures, we have some movies, we have some sound. And we got this, looks a little bit like a mosaic type of thing going on here. And we basically talk about like, how do we represent pictures, right? And in some ways, we're also talking about videos also, right? So if you look at video as basically a series of pictures, one right after the other, it's almost like a three-dimensional picture in that regard, right? So just look at it as terms of pictures. So each point in that picture, if you put in a combination of red, green, and blue, you basically end up with the ability to generate a wide variety of colors, right? So anywhere from black to white, right? And depending on how you mix these different combinations of colors, you'll get some variation. So for example, like, let's say I made it super intense, focused on green, and I made 0 for red and 0 for blue, then you're going to end up with basically the green color, right? And likewise, if I set these two, like red and green, to be 0, and I push the full intensity to blue, then you'll get blue, let's say. Okay. And then you can kind of imagine mixing these 3 different things. You'll get all different shades of different types of colors. And if you go to different websites, you'll see different things that will allow you to mix them in different variations to come up with all kinds of different colors. Okay. And this thing at the top right is kind of trying to show you the same type of thing. And notice when you mix all of them together, the center part here is white. Okay. And that's what this point is here. White is the full intensity of each color. Okay, so you put all of them and you put it all into the same quote unquote spot, you're going to end up with white. Okay, red, green, and blue, high intensity overlap is going to be white, right? And then likewise, if you set everything to be the absence of light, would be 0, you'll get black. Okay. And so a single color on a single pixel is going to be taking up 3 bytes. I'm not having you kind of memorize that for the class or for the exam, but we've done it in past classes. Basically, there's 3 bits in a byte. So a bit is a 0 and a 1. Okay. And so you look at those combinations, just like you look at those powers of 2, right? So 2, 4, 8, 16, 32, 64, it goes exponentially up. So you multiply all those together, then you get 2 to the 24, right? And that's how you end up with approximately like 16 million different possible colors. Okay, so there's 24 bits, right? You get 24 bits by saying there's 8 bits in the byte, right? So 3 times 8 is 24, 2 to the 24, and that's approximately how many colors you're talking about there. Okay. So there's a question here about the slides are posted in files. They're posted in files, but they're also posted in resource. Let me come back to here. So I kind of I tried to put everything here so you don't have to hop around between these different things here. So even here, like you can see, I put assignment here, I put the student schedule here, I put the Piazza here. So I tried to put everything all on the one page here. So for the slides, it's like right here, okay? I have to save them as PDF. I'm not allowed to save them as PowerPoints, but I tried the best I can to do everything here as opposed to having you click around on these different menu options here, okay? But if you see something here that I didn't put in, just let me know and I'll just stick it in here. Okay.
I'm sorry, Professor. How do you get to this page again? You go to
So in
pages.
home, like when you first come into Canvas for this class,
Okay.
you can see down here it says Lao section 6 to 8.
Yep.
Under course information. So I click on that and that's where I end up here.
It says I don't have access denied.
Oh, okay. Let me talk to you offline. Maybe we'll have to check how you're registered for the class to see if there's something screwed up there.
Oh, the people in the chat are saying they're denied too.
Really? They're denied into my page here?
I don't think anyone can view it. Like none of the students. I mean, at least the people in the chat and me can't.
Okay. So I'm not sure I'm going to fix it right now in lecture, but let me take a look at this after class and see if there's a permissioning thing on this page.
Okay. Thank you, Professor.
Yep. Okay. So yeah. So okay. I was saying that, when I look at these bits, 24 bits, you get 16 million possible different colors. Okay. So you might be wondering why we pushing all these numbers in here. So kind of like what in the old days, especially when space was more of a premium, but you can even say now space is a little bit of a premium, but not as much as in the old days. It was kind of important, right? So your phone maybe back then wasn't able to carry gigs and gigs of data, right? You didn't have stuff stored in the cloud or whatever. So it was kind of important for you to conserve space a little bit. So, if you take a picture with very high resolution, it takes up a lot of space versus like obviously with lower resolution, it takes up less space, right? So this just kind of trying to talk to that point a little bit. So let's say you have a picture which is made up of pixels, right? And all you do is just like your area calculation, right? So if you have a picture that's 479 pixels by 332 pixels, this is your number of pixels, right? It's just basically height times width, okay? This times this, okay? And so, how many pixels is represented by how many bits is going to say how much space this picture is going to be, okay? So you remember that we have the red, green, and blue component, right? And here's like the intensity for the red, the intensity for the green, and the intensity for the blue, okay? Then notice 255, that's a max number for this. So you would expect it to be very blue, right? Versus like this lower intensity for the red, which is 51, okay? So this is basically a 3 meg picture. Well, okay, 4 meg picture, I guess, right? So 4 meg picture, okay? So that's how much space you would have, which back in the old days, I guess 4 meg is a lot of space, right? So you would manage it in some ways. And there's different ways to kind of do compression and to kind of save space, which I'll go into in a second. But you do these kind of calculations to talk about how much space, either to store something or to transmit something over the wire, right? So send it across the internet or send it wireless or whatever. There's an idea of like these pipes and how much data you can get across the pipes. maybe one day we'll live in a world where it doesn't matter, like, we'll have infinite space, and then you won't have to worry about these space calculations. But for now, these type of things are somewhat of a scarce resource. So sometimes you make trade-offs based on the space usage. Okay. So again, this is just kind of repeating what we were saying before. So black is the absence of light. So that would be this 0, 0, 0, red, green, and blue, right? It's nice that make it color here so you can emphasize that point, right? So the red is all zeros, the green is all zeros, the blue is all zeros, okay? And then you have the decimals, right? And this would be anywhere from like 0 to 255. So you remember here, like this, right? 51, 153, and 255, right? This is the computer representation here. This would be like a human person readable representation here. And actually, even the hex is sort of like that, right? You remember we're using hex as kind of a way to shorten up rather than looking at all these different bits here. Like if you're a human looking at it, you're going to go cross-eyed here, right? So looking at in terms of hex as a kind of a way to compress this. So this is really the only thing the computer cares about, okay? But we've been doing the conversions to decimal and hex just to go through that. And then this is just repeating where white is the full intensity of each color, right? So that's 111 all the way through. That's the max number here, which translates into 255 here, right? And a lot of people, sometimes they get a little bit mixed up. They get caught up a little bit because they're thinking, well, actually it should be 256, right? Actually, it's not 256 because you start off with 0. If the number was starting from 1, then it would be 256, right? So you look at these numbers, let's say I use a smaller number, right? So you know that the exponents for 2 is like going 1, 2, 4, 8, right? So at that particular location, the number system wouldn't go up to 8 in that slot. It would only go up to 7, right? It would be going 0 through 7. Okay, and likewise, when you get up to 256, you're actually going 0 to 255. So that's why the 255 is the max. Now you look at hex. Well, what's the max for hex? Well, the max for hex is F, right? So then you would just say F and F across for the 3 colors here. Okay, and so I kind of asked, for the class what this question would be, and I'll kind of just talk it through. And basically, obviously the green is the highest intensity. These two are 0. So that means you should expect to see a green color out of this. Okay. So this is like the basics of talking about how do you represent a picture, right? And this is why we use kind of this mosaic thing, right? So you kind of look at each of these. Yeah, a mosaic is kind of built up like this. When you look at the pixels, it's sort of like being a part of a mosaic, right? So you have the pixels building up eventually into a picture, okay? Actually, it's a little bit harder to tell when it's all zoomed up like this. Actually, it's a little bit easier to tell that it's some sort of bird over here when it's like kind of smushed in together, right? And that's because like these pixels are kind of big, right? So when you get the picture bigger like this, you're going to need these pixels to be a little bit smaller, more numerous types of pixels, right? And that's why you guys probably see this at home, at your home computers, right? When you zoom in, you get like this big picture. Well, to get the same type of resolution where you could recognize that picture, you need a whole bunch more pixels, right? But if you don't have that much, you want to save space. That's why you get these little thumbnails and small pictures, and you end up with a picture you can recognize, and it takes up a lot less space, but then it's a smaller picture too, okay? So the key concept here, remember that pixels, add them together, and they're gonna become a picture like this, all right? Now, the other thing that we talked about is, one of the good benefits of having something represented digitally is the idea of like, quote unquote, perfect reproduction, okay? You have to factor in the space, like I just said. So when you look at, there's other types of effects, right? Both on the sound and on the picture perspective, right? So one of the things that they talk about is like, let's say I have a black and white picture. And I might look at different things like, well, how can I make it like color? Right. So you probably see there's kind of different websites out there that use like AI to try to like, you know, guess at how to replace those pixels, those black and white pixels or shades of black and white pixels, like gray pixels, to be a different color. Right. And then you can kind of make it a color type of picture. Some of them are getting quite good, actually. Right. So you know, what I'm showing you here is going to be very rudimentary type of things, like kind of shifting your pixels. The more complex you get with these formulas to modify all the different pixels, almost to the point where you're changing almost every single pixel in some custom way, makes for some pretty interesting effects and color. In this case, we're talking about black and white picture. Okay. But, you know, a long time ago, they had these things like red eye removal, right? So if you're taking pictures, you know, they have this function that takes out the red eye, right? That's, you know, been out there for a long, long time now. That's a simple thing, right? So you look for anything in your picture that is red eye, right? You know, pick the person and, you know, their eyes and there's red there, like take it out, right? There's other things like photo corrections, like something simple like this, like these little dots here. Maybe you want to get those things out. Due to color changes, artistic effects, which I'm sure a lot of you played around with things like that. That's part of what you get in terms of storing information in a digital way, in this case, talking about pictures, okay? So when we talk about pictures, there's a couple of dimensions. There's the idea of like making a picture brighter, and there's an idea of making contrast, right? Distinguishing, making it like sharper or crisper. You know, you can do things with contrast, the difference between the light and the dark, okay? So this is a point here, which probably a lot of you can kind of intuitively guess or figure out, right? So brightness talks about how close to white the pixels are. Okay. And like I was saying before, contrast is basically the difference between the darkest and lightest parts of the picture. So kind of like how much of a stark difference there is. I guess really it's just contrast, right? So really how much of a difference there is between the dark and the light of the picture. Okay. So let's step into this a little bit. Okay. So here's a very standard, very basic type of thing to brighten up the picture, right? So you want, here's a black and white picture, right? And you want to add 14 to each pixel. So what does adding 14 to each pixel mean? It means making it brighter, right? It's like, you can imagine if I just said, well, you know, let me set all the pixels to be 255, right? Well, then all of a sudden you're going to just get a white picture, right? So let's shift each thing up 14, right? When I say each thing, I should say red, green, and blue, each of them up 14, right? So that kind of will brighten it up, or intensity of each pixel, okay? So here they're showing like the value 195, 195, 195, and then that's kind of a representation of what that color is, okay? I don't know if it's easy for you to tell or not, but this is a little bit lighter, okay? So this goes to this when I go across the board, and each one I add 14, okay? This one's kind of hard to tell, but that's kind of also what's happening here too. This is like really dark, and this one is slightly less dark, okay? Now, look at the overall result though, right? So I basically add 14 across the board. That's very brute force. That's like the basic shift across every single pixel. And so what happens when you do that? So you add it to this, you end up with this, right? Very bright all the way across. That's like the brute force way of kind of adding brightness to the picture, okay? So you can say maybe something a little bit more custom. You can say, actually, for the darker colors, let's say the suit part here, I'm not going to add as much. Maybe instead of adding 14, I'm going to add like 5 or something like that. Or maybe I don't add anything at all, right? And then any of these other colors, I'll add something to it, right? So that kind of ups the complexity a little bit, or adds the sophistication a little bit of how you're going to manipulate these, right? And these are all very basic. Nowadays, you can get very custom. Like you can say, oh, this part of the picture, you want to do something, this part of the picture, you want to do something else. You know, and it's based not just on like the value of the pixel itself. In this case, let's say it's 195. There's other things that I might look at to try to figure out, you know, should it be doing it? Like you can tag like different parts of the picture. So there's some intelligence. So it can say, oh, this is someone's hair, right? And their hair normally is going to be in this range. This is someone's like suit, and then this is a range, right? So the more of this metadata or more information you get in here, then you can do your formula to shift based on like more sophisticated criteria. Okay, so contrast. So I think this one is pretty clear visually. You can see, right? So here's the original picture here. And kind of like what I was saying before, you can see it, there's like a little bit more of a pop, right? It's a little bit more of a stark difference, right? Between this light part here, and then let's say his suit, which is like one of the darker parts, right? In addition to his hair, maybe, okay? So that's where they're talking about the difference between the light and the dark part, okay? So here, like I'm saying, is you're not shifting the graph level to the right, which is kind of what you're doing back here, right? But just across the board, you just add everything, okay? You're not doing that here, right? But you're kind of looking at the difference. And just like what I was saying before, instead of adding more to the dark, we would add a little bit less, right? And that's what you're doing here, right? So adding a smaller amount to the dark pixel and then adding a larger amount to the light pixels, that will increase the contrast, right? The difference between the light and the dark, okay? So that's what they mean by contrast, okay? And this just kind of goes into like different ways you can do the shift, right? When I say shift, it basically means like taking this original RGB value and shifting it to this RGB value, okay? And then this is kind of adding a little bit more, right? So now you're saying, oh, look, let me look at the highlights, and then I'll apply this shift, right? Or change, they're saying here. And then I look at the mid-range, and then I apply this type of shift. And then I look at the shadows, and I apply this type of shift, right? So you can see how they're, you know, slowly but surely. The first example I show you is brute force across the board, shift everything. And you can see as we get more and more sophisticated, you're breaking down the ranges and then doing more custom type of shifts to it, okay? And then this is really just to kind of add some color to this, right? So just making a little bit of a guess. Let me add some red to it. There's some blue to it, not much green, okay? And then what do you end up with? Then you end up with something like this, okay? So this is like trying to show you step by step how you can take an image and add all kinds of effects to it. The basic type of effects that we're talking about now here is making something brighter, making something with more contrast, let's say. And then this last example is about adding color to it, okay? Like this, okay? Red, green, and blue, right? And you're shifting by these values. This is a negative shift, obviously, here, okay? All right, so digitizing sound. So I don't know like how many of you kind of know. So when you look at sound, probably, I guess, in your high school physics class, you basically have this idea of sound waves, right? And that's how you get things like, you know, stuff coming out of your speaker, going over the wire, like, you know, for your phone or something like that. There's like these sound waves, right? And, you know, how do you accurately represent that? Because, you know, that's basically an analog type of thing. When you hear sound, you know, it's an analog wave that you basically have. So how do you digitize that? Okay. And this is trying to explain that, right? So you have vibrations pushing the air, and then the pressure waves from that object will vibrate our eardrums to make sound, okay? And so that's what this is here. This is a sound wave over here on the left, right? And there's this idea of sampling rate. So you can imagine, so this is a low sampling rate. You can see like this curve, this sound wave is very like not good looking, right? It's very straight and whatnot. It's probably not, you would probably say it's not a very accurate representation of the sound, right? And then you have medium sampling rate, and then you have a high sampling rate. That means I'm sampling very often, okay? And you can see the curve looks fairly smooth compared to the first one, which has a low sampling rate. So therefore, when you look at your sampling rate, the higher the sampling rate you have, the more accurate representation of the sound that you get, okay? And obviously this is just a picture, so you're not gonna get like a whole bunch of sampling here, but you can imagine like, we're talking about thousands and thousands of samples, right? So that's one dimension. How many times do you sample the sound to get a reasonable level of accuracy in the representation of that sound, okay? And this is talking about file size and talking about how much space it would take to store all those samples, right? But here, sample per second, this is 44,000 hertz. Okay, so that's a lot of samples per second, right? But there's a trade-off there, right? So every time I take a sample, I have to store that information somewhere, right? So it's a similar type of thing to how many pixels do I store from the picture, right? So it's kind of analogous between your sound sampling to the number of pixels that you have for the picture, okay? So this is a standard type of rule for like how much sampling you should do. It's called the Nyquist rule, okay? Try to remember this one. This is important, right? So Nyquist rule is a very standard type of thing. It's not a hard thing to remember, right? So basically what the Nyquist rule is saying, well, how many times do I have to sample something to get quote unquote appropriate representation of the sound, right? And so here we look at a very common thing is, well, can a human hear the sound, right? Right. Most of the time we're digitizing stuff for humans to listen to, right? So humans can hear up to basically around 20,000 hertz, right? A lot of humans can't actually really hear up to 20,000 hertz, but let's say it's 20,000 hertz, okay? So all the Nyquist rule is saying is that, well, for me to get a good representation for human consumption, I need to do 40,000 hertz as your sampling rate, right? I have to sample 40,000 times, right? To get something that is a reasonable reproduction of the sound for human consumption, okay? So I know it says 44,100, but just say 40,000, right? 40,000 hertz is good enough. It's approximately 2 times the range that you want to capture for. In this case, 20,000 hertz we want to capture for human listening. So I'm kind of simplifying it or just summing it up for you tightly on this. Nyquist rule, remember that whatever sampling, maybe you want to sample for a dog or something, right? But let's say you're sampling for a human, it's 2 times 20,000, basically 40,000 hertz is your sampling rate. Okay, so you need to program your microphone, your computer to sample for 40,000, okay? All right, and then this just talks about like how much space do we take up per sample, right? So there's this idea of like bit depth right here. So just like for the curve up here, when you do the sampling, we're taking all these points along the curve like this, and then you kind of form it like this. So it's almost like slicing up and down, all right? The bit depth is the other way. This is like 2 dimensions, right? Now you're kind of slicing across like this, Okay, so same type of thing, right? If I only use a bit depth that only captures this many points, again, I'm going to have a problem in terms of accurate reproduction of the sound. So the more of these slices I take horizontally, again, I'll have a more accurate sound or representation. So that's what they talk about with bit depth, right? So each of the samples that I take, how many bits do I want to represent? Right. So if I go to like the most extreme example, like a very basic thing, let me say I only take 1 bit, right? Like 1 bit is either a 0 or a 1. You can imagine what kind of sound I'm going to get from that, right? It's not much of a sound, right? It's either like 0 or like whatever, like some loud sound, right? I take more and more bits, then I can take more and more of these slices, right? And so kind of what they're saying for us, for audio digital representation, we're usually going to use 16 bits, right? So that's 2 to the 16th in terms of the number of these slices that I can take. So between the Nyquist rule, talking about how many samples that we can take, and the bit depth of 16, that gives you a fairly accurate reproduction of the sound, okay? So I kind of jumped over to here, but this is the main point here. There's always a trade-off, right? So if you want unlimited number of bits for the samples, you're gonna have to take up a huge amount of space, right? So there's always gonna be that trade-off, and probably the constraint that we can leverage here is that people have a certain listening range. Humans have a certain listening range, so you don't need to have like infinite amount of samples, infinite bit depth, because humans can't hear that much anyway, right? So you only need to represent a certain amount. Okay, and some of that plays into the compression for pictures and videos also, in terms of what does the human eye see and what does it perceive more easily if you were to take a shortcut there, right? And we'll get into that in a second. Okay, so this is the digitizing process. So you remember I was saying like a sound wave looks like this, right? So within your microphone, it'll take that analog wave and kind of go back and forth and kind of pushes zeros and ones and converts that analog into a digital stream, right? And that's where you get all these zeros and ones. And then likewise, you take these zeros and ones, it comes out to here, it goes and gets converted to analog wave, which then plays over your speakers and then comes out like this, and then ultimately pushes air into your ears, which does another conversion so that your brain can process the sound, okay? So basically that's what this is saying here. The sound is picked up by the microphone, transducer. You don't really need to know that. Just know that the microphone converts it from an analog to a digital, right? So you have an analog digital converter, takes the continuous wave, samples it, like we were saying, Nyquist rule, 2 times 20,000, which would be 40,000, and then outputting each sample into a binary number. Then the binary number goes over to a digital analog converter, makes it back into sound waves, and out comes the speaker, okay? So talking about the advantages of digital sound, you know, you can do different types of effects also, same thing like the pictures. You know, I don't really know if this is like an advantage or not to remove waves that are too high or too low for humans to hear. Maybe if you're talking about how to store something in an efficient way, but in terms of accurate sound representation, yeah. You know, once you store it digitally, as long as you capture that range up to 20,000 hertz, you're good to go, right? You know, the overlay of small errors, so you can obviously take things out, right? You know, maybe a lot of the music you listen to right now, you can do things like auto tune and stuff like that. So there's all kinds of effects you can do with the sound, right? Similar way as you can do with the pictures and stuff, okay? And then when I look at video, the way I like to look at the video is just basically a series of pictures, okay? So when you look at these, videos, there's a lot of different things that apply in a similar manner to a picture in terms of like effects or in terms of like compression, right? It's just that you have an extra dimension there. And I'll step into that in a second here. Okay, so this pixels per frame is basically the same thing as me calculating how many pixels per picture, right? Per frame, think of a frame as a picture, right? So you take that 640 by 480 to get that, right? And then you take this and multiply by 24 bits, remember 24 bits, and you get 7 meg, right? A bit over 7 megs, okay? And then you look at, well, how many of these frames am I going to play for the video? Okay, so you have 25 frames per second as your frame rate here, and so you take your 7 megs times your frames to come up with about 184 per second. Okay, so all of this up to here is basically you saying this is how much space a picture takes, right? And then you say, well, for a video, how many times am I showing that picture, right? I don't know if when you're younger, you maybe have like that thing with multiple pictures, and then you can like play the pictures across and it looks almost like a video, like someone's like moving or something like that. So the first 2 lines is the calculations you would do if you were just calculating how much space does a picture take up. And then you just say, well, how many of those pictures together makes my video? In this case, we're saying 25 of those pictures per second is making a video, right? So that's why you just take that number and multiply it by 25, and then you get that, okay? And then the last bit was, okay, you have this 184 per second. How long is this video, right? So in this case, we're saying this video is 3,600 seconds, okay? Which is an hour. Okay, and then you end up with 82 gigs. Okay, obviously, when you're actually doing this for personal consumption, I doubt your videos are at 82 gigs. Maybe you might have a video that takes a gig or 2 gigs for a couple-hour movie, maybe. Depends on how much you jam into there, but it's usually going to be a lot less than 82 gigs, right? So there's some compression going on here, right? And we're going to step into that in a second. So this is another important concept. It's compression, right? So, we don't have unlimited space, or we're trying to ship a whole bunch of data over like old technology, over wireless or whatever, right? So when you get to these type of trade-offs, that's why you get into things like compression, okay? Now, there's different types of compression. There's lossless compression and there's lossy compression, okay? Lossless compression means that I can still accurately represent, let's say, the picture or the sound perfectly, right? Even after I compressed it. That means I can go backwards. I can say, okay, this is what it is, and then I can go backwards and I haven't lost anything, right? Lossy means that once I've compressed it, I can't go backwards. I can't like get it back to its original quality. I can't accurately reproduce it 100%. So that's what's meant by lossy compression versus lossless compression. Okay, and then over here on the right is some examples of lossless compression and then lossy compression. Okay, I'm not going to go through each one of these, but I'm going to talk to you some of the strategies that people use in terms of lossless and lossy compression. Okay. So audio compression, they do things like take out sounds that are too high or too low to hear. Okay, and then the strategy when you look at videos or pictures, when humans look at something changing in brightness or luminance right here, they tend to pick that up pretty easily, right? That kind of jumps out at them, right? But they're not as sensitive to some small differences in color, and that's called chrominess. Okay, So, if you're going to make a trade-off in terms of where you're going to like kind of cut corners to kind of save some space, you're going to probably do it around the differences in color. Okay. You try your best not to mess around with brightness, because brightness, people can pick up on that pretty easily. Okay. So this is like kind of the strategies you look at in general, right? There's a couple different things to look at here. Okay, so this talks about different things. You probably have been using different things with YouTube, Netflix, or whatever. So the idea here is that there's a lot of, you can imagine we have zeros and ones, right? So there's a lot of repetition, right? If you look through any data stream, there's like a whole bunch of like potential repetition. So let's say I have like, 0, 1, 0 as an example, right? And let's say for whatever reason, there's a repeat of that sequence, whether you're looking at it in 2 dimensions or 3 dimensions. Let's say the sequence 0, 1, 0 is repeated 30 times, okay? So instead of saying 0, 1, 0 30 times for that dimension, whether it's like a 2-dimension thing or a 3-dimension thing, like you'll just say 0, 1, 0, and it goes for 31 times, right? So that's one way to save a huge amount of space. Okay, you save a lot of space by identifying all of these repetitions, and then just saying, well, this is how many times it repeated, and then you can reproduce that pretty easily, right? You don't lose anything. So this is an example of lossless compression. Okay, when you look for these duplicates, because you're not sacrificing anything to say 0, 1, 0 31 times versus there's 31 0, 1 zeros. Okay, it's the same thing, right? Okay. Okay, so this is kind of getting closer to the wrap up on this part here. So this basically just talking about like everything is a bit, and how does that map to like the human representation of it, right? So I didn't make it as a requirement for this class, but we talked about the ASCII conversions, right? Extended ASCII and whatnot. So you can look at something here and saying, well, this is mapping 65, or this will be mapped to A. Okay. And then you can also talk about sampling for a piece of sound. Remember 44-100, that's our sampling based on Nyquist rule for humans, right? And then you also have RGB for a pixel, right? They're saying a single dot here, right? But a pixel for a picture, right? Or it could even be a part of a movie, right? So 65, 200, and 12, right? And you have the amount of redness on the picture here, okay, in the red, all right? So this is another thing that I took out of the curriculum, so you don't have to worry too much about this. So this just, it's kind of like a more of a theoretical type of thing. I don't really know if there's like a practical application for this. So that's why I just took this out. So you can ignore this. Let me just delete this slide here. So there's the idea of latency and bandwidth. Don't worry too much about this. I took this out, but it goes to the point before of what I was saying here. Why do we jump through hoops to do like compression, right? And why do we make these calculations for how much space something takes up? Well, it's because we don't have unlimited bandwidth, right? So like I was saying, you can have like this ginormous, super accurate movie or picture or whatever, but everyone's going to choke trying to download this thing onto their phone, let's say, or stream it. So that's when you get into different things, because you don't have the high bandwidth and that leads to not being able to get low latency. So that's the main point here. I wouldn't worry too much about this, just to know, bandwidth in terms of how big is your pipe, right? Like bandwidth is like, you think about how much data I can stick somewhere, and latency is how fast it can get there, okay? We want it to be fast, right? We want to get, like this ginormous movie, like in no time flat, right? We want to stream it without any lags or anything like that, right? So that's all that is, right? So that's a challenge, right? But I didn't think it was that big of a deal, so I didn't include that in the exam processing either. Okay, so these are just type of checks here. This is kind of review some of the stuff we talked about up here. We did those calculations to say, okay, the colors that make up a pixel, like what are they, right? How many colors are possible? What happens when you don't have any color, absence of light? And then by the other extreme, what happens when you have the maximum intensity of light, right? Right. And then let's say I have maximum intensity. What's it represented in decimal, right? These are the type of things that don't be surprised if we ask you that on the exam, right? Okay. How do you decrease the brightness? How do you decrease the contrast? How do we colorize a black and white photo? These are the things we just did in class here, right? So we digitize sound, right? What are we taking, right? We're going to sample, right? At what? At some sort of rate, right? What's the rule for determining number of samples, or the rate of samples, I should say, right? What is the bit depth, right? So these are important concepts. They're going to be on the exam, so take notes, do whatever you have to do. Make sure you can answer those. What's the difference between lossy and lossless? Latency, difference between bandwidth and throughput. I'm not going to ask you that, so I'll take that out, okay? And these are kind of summing everything up, okay? So we're getting close to the break here. So I'm going to give you guys a 10-minute break. And what I want you to do during a 10-minute break, it should be easy, right? Just go into, crap, I forgot you guys don't have access to this. Maybe I can figure out a way to give you access.
Professor, those games are in the announcements, I believe, that you sent
Oh,
out.
yeah, you're right. That's it. So in the announcements, I put it in here also. Yeah. So if you can go to the games here and just do a couple of them and just maybe take a screenshot or a picture of it and then send it to me in email, just do exactly what I did before, right? So let me see here, binary conversion game, right? So when I'm here, just kind of show me that you did something like this. So here's the 0, right? So I just did this, boom, something like that. You don't have to do all of them, right? Just do a couple, whatever. Do like a picture of it and do a picture of the other one too. Should be nice and easy. And we'll reconvene like in 10 minutes, okay? All right, so I'm gonna leave you guys to that. Send me email with those two things, and then we'll kick off with the next lecture in 10 minutes. So it's 7:01 right now. Okay, I'm gonna give you less than 10 minutes. I'm gonna say 7:10. I'm gonna restart, okay? All right, thank you. Okay, so welcome back. See, we're at 7:10 here. So we're gonna do chapter 3. So the other 2 chapters are gonna be stuff that sets us up to start doing HTML. So we'll be doing stuff like how do you do web searches and then doing the HTML page. So we can save that as a separate discussion for Wednesday. So for today, the remainder of today, we're going to cover chapter 3. So basically it just talks about basically how things kind of hang together on what we think of as the internet. So how do we communicate, the idea of like the different destinations on the internet. So the idea of like addresses and what's the directory of those addresses? How do we, how do we take ownership of those addresses? How do we look up who's at an address and stuff like that? So you have, these domain names, you have these domain name servers, how do we talk? How do we send emails or other information across it? How does the hardware facilitate this? All that type of stuff. So that's what chapter 3 is going to be talking about. The heading is called networking. Okay. Actually, before I do that, just as a reminder, in case people are wondering, is there reading for this class or not? So if you go back to here under course objectives, and you can see the parts where I kind of crossed out things to take out a normal class. You can see different things like the vocabulary. These questions here, take a look at them. If you're stuck on any of them, send me an email, send the TAs an email, and we can respond to that. And you basically can see all the different points here. This is part of the resources. The text questions. This is where, if some of you have different versions of the book, like an older version, this is where you might not line up 100%. So if you kind of get stuck, just like let us know. We'll see if we can map it to whatever the right questions are. Okay. But yeah, it goes through the chapters, right? Here's the chapters and all of the different vocabulary terms you should take a look at, minus the ones that I tried to X out here. Okay, so that's kind of things you want to look at in terms of like reading and whatnot, or resources. Okay, so let me come back to here. And all right, so communication types. You probably have seen this before, right? You've talked on the phone and, both people can talk at the same time, right? So that's called synchronous communication. That means like, just like in a big Zoom room or something, everybody's like talking at the same time, right? And then the idea of asynchronous would mean that I send you something, maybe I send you an SMS or something, and you can choose to respond to me 10 minutes later, an hour later, a day later, whatever. And that's like asynchronous, right? You send something, at some point the other party will return something to you, a message to you maybe. Okay, so that's asynchronous communication versus synchronous communication, which the example there is usually like you're on a phone talking to each other. Okay. So, how does information get from point A to point B on the internet? And, they kind of draw the analogy to you tracking like a package, right? Whichever provider you use to ship the package, right? UPS, FedEx, whatever. They'll have these things where they'll kind of send you like a link and you can see it going to all these different destinations, right? Along the way. So going from point A to like point B, let's say at the bottom, it'll take these different hops, right? It hops to here, all these different places along the way. And it's just telling you that, oh, I got to here, stuff like that, right? And so when I look at the internet, here you are, you're sitting at your computer over here. And then there's like maybe a web server, right? These days, probably not, right? Probably it's more like a cloud or something like that. But, you don't have a direct piece of wire that goes from your computer to the web server, right? You're having a whole series of other computer hardware or machines or servers that are between you and this web server over here, right? So let's say this is you over here, and this is Amazon or your bank or whatever, right? Over here, you do not have a direct connection, right? And the whole idea of the internet is the ability for all of these different addresses or points along the way to work together as in a collective way to form the internet, right? And so I might say, I want to go from here to here, and along the way, I might take this type of path here, like this path in red here, or maybe my request goes through here, right? Or goes through here. It can go any number of ways, right? So ultimately, people know where you want to go, and how it gets there. It's sort of, I wouldn't say at random, but it's sort of like, from your perspective, probably it looks random, right? It just goes all over the place by the time it gets to here. Okay. So how does it look like you stay connected, right? So you're doing a transaction on an e-commerce site, let's say, and you're making some querying. In this example, they're talking about like your online banking, or you're purchasing like a concert ticket or something, right? So you might take ages. You might be there. You might go out and like go check whether you have some money in your bank account or something, whatever, right? The screen or your phone, right? It's maybe on your phone, or maybe it's on your computer. It looks like you're connected to it all the time, but in reality, there's no way that could be, right? Because these sites are taking requests from like thousands or many thousands of people at the same time. That's how you get into like a denial of service attack, right? It cannot hold all those open connections, like everybody hitting the site, and you maintain an open connection for everybody. Like the internet, well, in this case, the server would never work, right? It would just be a disaster, right? So, there's things that it does to simulate or remember different things, so that when it comes back to you, right, it does like a round robin, right? The server will kind of say, oh, what's your request? And you might say, I'm thinking about buying blah, 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 right? And can you give me more information about this, right? And then it goes to, say, okay, no problem, just hold on a second, right? And it'll go and like go into its database to kind of fulfill your request. But at the same time, it doesn't hold that connection with you. Then it just opens up another connection to someone else who's making another request. Maybe they're making the same request, maybe they're making a different request. And it does that round robin across a whole bunch of people at the same time. And so when it comes back to you, how does it remember that, hey, I was just talking to you and you want to know about blah, blah, blah concert, right? And that's cookies, right? So cookies are sort of these little things that kind of store bits of information to help the provider, right? Let's say the person that is the server is trying to fulfill your request information, so that it knows, oh, you were the person that asked me for this, and this is your answer, let's say. So that's why probably a lot of you hear about this, right? And you probably see it, right? It's been in more recent times, they've been pushing a lot of different things to kind of remind people that there are bits of information, some of it kind of pretty private to you, that's being stored about you, right? It's not just like I do something on the internet, then once I'm done with that transaction, it's gone. It's more likely the opposite of that. It's more like your information is all over the place. And one of those places where you have some of that information is in the form of cookies, okay? So that's what a cookie is, right? You can see the server stores a file on your client, which is you, with information, okay? And it's related to interactions, okay? Now, in a good way, it would help to facilitate the transaction. In a bad way, that information can be, collected and used against you in a malicious way, right? So I need to be careful with these type of things, but I won't go into that now. That's going to be something a little bit later on. But just remember this, whenever you make a connection to something over the internet, it looks like you're like talking to whatever website for the whole half hour or however long you're on there. But in reality, you're not. You're only making a very small few second interaction with the website. In the meantime, it's hopping around and talking to other people all at the same time. Okay. So, there's a video that talks about like IP addresses and stuff. I don't think we need to watch the video. We just kind of go through what IP address is. IP address is basically every single thing that you can access on the internet. Like when I say thing, I mean a machine. Whatever type of processing that you can do something on the internet has to have an IP address. Okay. And IPv4 is like an older version, obviously, right? It says V4 means version 4 versus like the latest one, which is version 6, okay? And all that means is that in more recent times, they have this idea of Internet of Things, which means there's like a whole bunch more things that are addressable on the internet. So you start to actually run out of addresses. And that's why you came up with IPv6, okay? So this is the idea around IP addresses, right? So every single website has an IP address, right? So this is an IP address, right? And then, like I was saying, IPv6 gets you even more addresses, right? 128-bit, right? Versus IPv4, okay? So this is a huge amount of addresses that you can go at, right? But we're talking about this address here, and this steps into like this idea of like, you know, we obviously don't, well, not obviously, we don't think of things in terms of IP addresses. We think of things in terms of like the domain names, right? So there's a mapping between these IP addresses to domain names, okay? For the ones that we usually go to, right? There's other IP addresses that it's only computers that go to them, not humans, right? So they don't particularly care that much. So like I said, really you think about your home address, right? You think about like all the different pieces of your address to identify exactly where do you live, right? The town that you live in, the state that you live in, the street you live on, and then the number of that street that you live on, right? So in a similar way, you're kind of thinking about IP addresses. Each of those sections on the IP address is kind of going from top down in terms of like, let's say the top level granularity for us is you being in the United States, right? And then within the United States, then there's the states, right? New Jersey, right? Let's say. And then within New Jersey, there's like some cities, right? And then within the cities or towns, right? Then there's like some streets. And then within the street, there is like a particular house address, right? The IP address works in a very similar manner, okay? And working your way from top down. I'll give you an example of that in a second, okay? So you guys probably see this, right? I mean, Rutgers, right? So you have edu, right, for Rutgers, right? And then you have com, and these are the historical, what they call top level domains, right? Obviously, like in recent times, you probably have noticed like there's more and more of these just because there's so many things that are getting hooked up, people accessing it, that they were actually running out of these things. So that's why I had to come up more of these things, right? But these are kind of like some of the early ones that they started off with, right? And you know, this is probably like these two up here, edu and .com, are probably very commonplace to almost anyone who's done anything with the internet, right? But then now you got expansion on some of these. So you may or may not have seen some of these other new ones that have come in. These things with the 2-letter country designators, they've actually kind of been around a little bit longer. So, you know, basically if it ends in a CA, it's Canada, like JP is Japan, you got the UK, you got France, blah, 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 right? So any of the country specific ones, again, that's just another way to expand the number of domains that you can have, because the original ones are probably maxed out or getting maxed out at this point. So it just opens that up a little bit. Okay. So, you know, they've broken it up by different color coding to kind of go at the same thing that I was just talking about in terms of like country, state, city, street, and then address here. You have different levels separated by these dots here, right? So you have like the dot here, and the dot here. And then it kind of goes into each of the different levels, right? So EDU is obviously very generic, right? There's a whole bunch of EDUs, right? And then you go down to here, this is kind of like saying which EDU, right? In this case, University of Washington, right? Well, but then within University of Washington, there's like a whole bunch of departments, right? Well, we're talking about the computer science department, right? And then you say, well, within the computer science department, there's a whole bunch of computers, right? And so then here's the specific name of the computer, right? So it's sort of like high level granularity and working your way down to the lowest level of granularity. Okay, so EDU, Washington, computer science department, and then the name of the computer within the computer science department. Okay, this visualization kind of helps to kind of maybe show it some more, right? So this overall big green cloud is your EDU. And then here you have like the Washington, this is University of Washington, then you have Princeton here. And then within here, you have like these little mini clouds here, which would be like departments. And then the lowest level granularity are the specific machines here, right? So this is Tracer, and then this is Spiff here. And then this is, for example, illustrative purpose. Obviously, there's a whole bunch of these little things within Princeton also. But this just to show the difference between the different EDU within EDU, right? The different universities. And then you kind of drill down into the Washington University to get this, okay? So again, looking at it from a hierarchical point of view, right? So from the top down, right? Again, you have all of these top level domains. And then within the EDU one, then we broke down into Washington and Princeton, and then Washington into department, and then within the department into the specific machines. Okay, so that's how this hierarchy works, right? And it goes from the right to the left, right? So boom, 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 and separated by dots. Okay.
Professor, I have a question.
Yes.
What about I see things like .io. Is that a different type of domain?
That's a good question. I'm trying to think. Is .io? I have to check on that for you. .io sounds familiar to me for some reason, but I don't remember what that refers to.
It's okay. I was just curious.
Yeah. No, that's fair enough. I can check for you. I'll come back in the next lecture or something with that one. Okay.
Okay, thank you.
All right. And so like what I was saying before, each of these is really more for human consumption, right? Like the computer doesn't care about these names here. What the computer cares about is these IP addresses here. So if I look at the computer is saying blah, 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 dot, blah, 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 dot, blah, blah, right? But for a human, we have no idea what the heck that means, right? And so that's why you have these idea of domain name servers, right? You don't want to be sitting there typing in these IP addresses, right? You want to be typing in something like this, maybe. So you have to have, they drew an analogy, if anyone kind of remembers what a phone book looks like. This is something like that, right? So there's some sort of directory. That's all you have to know. There's some sort of directory that takes what a computer understands, what the internet understands in terms of IP address, and maps it to what people would know, Amazon.com, right? Rutgers.edu, something like that. So that's what these domain name servers are, right? And then there's like these, commercial type of places that will do things for you, right? They'll help you to register. Let's say you want to create a new domain name, right? Assuming that no one else has used that domain name before, then you can register it, right? So then you have to pay for it every year and all that kind of stuff, right? You happen to pick a good domain name, maybe someone else will buy that domain name from you or whatever. But you have these various services that will offer services around this, right? Maybe they'll help you set up a website. Maybe they'll help you lock up your domain name. They'll help you to set up things for like security, right? Like SSL and stuff like that. There's all kinds of businesses that have kind of sprouted up around like what I would call directory infrastructure or whatever you want to call it. Like this is what it is: domain name servers maintaining this mapping of IP addresses to these domain names. So there's a business around this. Okay. Yeah, I'm not really going to talk too much about this, right? All you have to know is like your local area network is if you're down at the computer lab and you're futzing around on there, that's your local area network, right? All your computers are connected to each other there. They can talk to each other and do whatever. And then if you want to go out to whatever XYZ university across the other side of the country, you want to go to UC Berkeley or something like that, you're going to connect up through the wide area network, right? So that's kind of the main thing. I wouldn't worry too much about this, right? Just know that local area network is kind of, as it says, local, right? Your computer lab or something. Wide area network is more thinking about like, across the United States, let's say. All right. All right, so this part is, I'll try to simplify this as much as I can for it. So TCP/IP is basically how we send, it's a protocol or basically a guideline on how do we send information from point A to point B, right? So this is, they draw the analogy of like you having a book, right? Maybe a novel, and you basically take out one page at a time and you send it, right, on these postcards. And then on the other end, oh, I lost a slide here, but anyway, so on the other end, someone else gets all these postcards, right? So you imagine you have a 100-page book, right? And I create 100 different postcards and I send them to my destination. They get it, right? There's got to be something that kind of tells them how to put it all together, right? But assuming that they get that, they have something that will let them know how they're supposed to put all these postcards into the right sequence to recreate your book, basically. And the thing is that they would also know if there's a page missing, right? So it would send something and you might say, oh, well, I got 99 pages or I got 98 pages or something like that. I'm missing page 7, I'm missing page 9, right? And then it would come back to me. I said, oh, something must have happened. I must have lost it along the way. It fell out somewhere on one of those servers on the way from point A to point B. And so they would go ahead and tell me, and then I would resend it, right? So this is like this protocol, right, or this guideline on how to send messages from point A to point B is what they call guaranteed delivery. Okay. And the reason why they can guarantee delivery is exactly because of what I just said, where, when you get to the other end, you get to point B, you collect all these postcards. There's a way for them to look at it and say, oh, I got all the postcards except for page 7 or page 9 or whatever, please resend, right? And then they'll resend it. Okay. So each of those postcards in computer terms or technical terms is called a packet, right? P-A-C-K-E-T. So you send these packets from point A to point B, and then there's, like I said, a guideline on how to put those packets back together in the right order. And if something fails along the way, there's a protocol or a guideline for the sender to resend those packets again. Okay, and that's why it's called guaranteed delivery. Okay, so those are the main things you want to get out of like the TCP/IP. TCP/IP from point A to point B. The sender breaks it up into packets. The receiver puts all those packets back together again and tells the sender whether I got everything or I'm missing something, and to resend it. Okay. It's a little bit simplified, but that's pretty much how TCP/IP will work. Okay. Ethernet, not much to it, right? You just, you kind of look in your computer, you'll see like an Ethernet port or something maybe, right? That's just really like basically your high throughput wire to connect yourself to the other areas of the internet or on your home network, let's say. So internet communications, right? So this top part is probably what a lot of you have, right? So your house or your home or whatever. You'll have like a modem that will get you to your internet service provider, probably Optimum or something like that. And from there, there's a gateway, which basically goes out to the internet, which there's a whole bunch of other like computers and gateways and whatnot. So that's how everything kind of hangs together. Okay, within your house, you probably have Wi-Fi or something like that. That's something else, but ultimately that will connect up to a router, and then that will connect you up to the internet service provider, internet gateway, and then ultimately the internet. Okay, like I said here, if you're at the Rutgers campus, if you go down to the computer lab, you're probably sitting on a local area network where all the computers are kind of hanging together like this. There are certain protocols on how the computers can all share this wire going out to this internet server. Okay, so like if you look at this, ultimately all of the traffic kind of merges together from your house into this, and then it comes out to here, right? It's kind of simple, right? Here, you can imagine how many computers are on the local area network, could be hundreds, right? How does it all come together and go out through here? There's like different protocols on, basically who can have the conversation, right? You can't have everybody screaming into this at the same time. There are some protocols on how to interact, but that's probably beyond the scope of this class, so don't worry too much about it. All you need to know is that from here or here, there's basically almost like an aggregation service to kind of pull everything together and then ultimately connect up to the internet. Okay. So yeah, just what I was kind of talking about, what you probably have at your house maybe, right? So your modem comes in from your internet company, and then you have a router. Maybe you have a wire that goes from your router to your desktop, or maybe not. And then you have a wireless setup that you can do the Wi-Fi, hook up your phone or hook up your laptop computer. But it all comes together here. Router, that's exactly what the name means, right? It routes things, right? So it will route. Your modem does some conversions, and then you're off to the internet. And there's like all this back and forth to it. Okay. All right, and then this is just a rehash of what I just covered here. I think I covered all of these here. But if I didn't, just make sure, let me know. Path name, I didn't cover it in this class. I'm going to cover in the next class. There's a couple of different things related to what we call absolute path and relative path. So even though it's on this slide, don't worry about it. It'll be on the Wednesday lecture when I talk about it. But I think I should have covered all of these for the class, except for this one, describing a page by HTML, including the advantages. I'll talk about that also in the next class. The next class will be more dedicated to HTML. Okay, so this is more of a networking discussion. So that's why I talked about these things over here. Okay. So anyway, I haven't checked my email, but take your time, try your best to kind of send me like a screenshot. I realized that the numeric conversions is like a little bit of a shock to some people. So do take some effort to kind of, do those couple exercises on the games, send it to me. If you really have a problem understanding how to do that, you really need to talk to the TAs or myself, because it will be on the exam in a couple of different questions. You're going to need to do the numeric conversions. You're going to need to show the work for it. So it is important that if you don't get it, you got to come to us and, let us know. Okay. And then, let's get this stuff down pat. Then we can go into HTML, and then we'll be going into JavaScript, and then we'll go into Excel and whatnot. Okay. Let me see here. Does anybody have any questions I can answer about like the 2 chapters I covered today?
I don't have a question about the chapters, Professor. I mostly wanted to ask instead about the exam, if any practice exams would be made available prior to the exam coming up.
Yeah, so that's a good point. I actually was tweaking. So let me see here. Give me a second here. I thought I had it in one of my tabs here. Oh, here we go. Here's a sample exam here. So we have the sample exam here. I'm just kind of maybe tweaking it a little bit. Now, keep in mind, these sample exams are kind of coming when we were doing like the normal exams, not the online exams. But I have like some problems trying, well, I shouldn't say we have some problems trying to pull out the sample exams from the Canvas in this type of way. So I basically have to, it's the same questions, but I have to show you the questions in more of like a paper format. So I will try to get this over to you. This will be the sample exam of the material that we will be covering for exam 1. Okay, so I will be getting that out shortly.
Okay, thank you.
Okay. So should we download Microsoft Office? Why not, right? So Rutgers has a site license. That means everyone can get the latest version of Office or whatever version Rutgers happens to have. You can run it online, but when you run it online, you don't get all of the features of Office. So, which may be kind of good enough for what you need, but I think for the Excel stuff, you do need the version that you can download onto your computer. Now, if you have a problem on your computer where for whatever reason your computer doesn't have enough space or something like that, let the TA know or let me know, and we'll see if we can work out something. But I kind of would say, unless there's a compelling reason, you should try to use the site license from Rutgers to get the free version of Office. And you should try to use the one that you can download onto your computer. Okay, but let me know if there's any problems. And again, we'll deal with it. Cool. Any other questions?
I have one real quick.
Yes.
So back in chapter 8, back in the photo of the hammerhead shark, it says that there's 8 bits times 3 colors. How are there 8 bits? I couldn't figure out where the 8 came from.
So there's 8 bits in a byte.
Okay.
Yeah. So there's 3 bytes. So that's like 3 times 8.
Okay, that's what it was. It was bothering me because I couldn't figure it out.
Oh, okay.
Right.
Yeah.
Thank you.
I know it's like, so the class, we go into a little bit of like computer history and stuff like that. There's like some historical reasons why like certain things have worked out the way they are. So yeah, it's just a thing that's been out there forever. 8 bits equals to 1 byte, right? So people talking usually in terms of bytes on things, because bits is like very small. That's just 0 and 1, right? So yeah, so when you talk about these colors, if you talk about it in terms of bytes, then you just have to multiply it by 8, right? So if you have 3 bytes, then it's going to be 3 times 8, which is 24 bits. Okay, cool. Any other questions? Cool, good. So thank you for bearing with me for these 2 hours. Next class, like I said, we're going to dive into HTML. So looking forward to catching up with you for next class. do try to send those numeric exercises to me. If you're really getting stuck, you need to let me know ASAP so we get you straight before we move into the other stuff. Okay, and if you want to do office hours, make sure you send me email so I can reserve a slot for you. Okay, all right, thank you and have a good night.